Hello from the Mechanical Structures Division. I'm Greg Santiago, leader of this division. I was in charge of designing and manufacturing the newest member of our family, Hydrus. Along with my fellow division members, we decided upon various materials and designs for every mechanical and structural component utilized in Hydrus. We also conducted destructive and non-destructive testing to find out the limits of our design to better improve our previous AUV. What you're about to see is the result of our passion to own the devs and create the best possible version of Hydrus and a platform that will carry our team for the foreseeable future. An AUV's hull has to surpass certain requirements in order to excel in the RoboSub competition. It has to be waterproof to a certain depth, which would be 18 feet from the constraints of the pool used in the competition. It has to protect sensitive equipment like cameras or sensors. It has to provide space for thrusters, sensors, and other equipment that may be necessary to complete the mission given to it. It also has to provide connection points that allow power and information to flow in and out of the hull without allowing water or air to bleed through. For this competition, a buoyancy of at least positive 1% is necessary in case of critical failure to be able to recover the AUV safely. There are also more mission-specific requirements, like the addition of torpedo launchers for tagging a target, or the inclusion of an actuated gripper for manipulating objects like switches or levers. All of these are addressed and implemented in our design. To provide appropriate waterproofing, the team opted to utilize a conjunction of both retail and in-house components. We used two blue robotic 6-inch acrylic cabins, one to house the electronics and the other to house batteries and power distribution systems. These two cabins are jointed in the center by a custom-designed cabin made from aluminum 5052 that provides ample space for connections and also doubles as a heat break to better manage the heat output from the battery packs.
The penetrators that are protruding from the hull act as fins and provide greater heat exchange capacity. While this is only a bonus for the competition, it allows us to think of future work and applications that we may give Hydrus.
A smaller 2-inch acrylic cabin is positioned in the lower bow of the AUV that houses the stereoscopic camera. The smaller cabin is connected through a rubber tube joined between the main cabin and itself.
The positioning of the camera along with its rotating mechanism allows Hydrus to have a full frontal and bottom view of its surroundings. This greatly increases our capacity for surveying and mapping out the environment or mission area or obstacles that the mission may provide.
The DPL sensor is placed below the main cabin in the geometric center of the AUV and is protected on the sides by the HDPE light components. The thrusters of the AUV are placed in a vectorial arrangement all around the AUV in order to provide the ability to move with 6 degrees of freedom. These are either bolted directly on the HDPE chassis or connected through carbon fiber reinforced 3D printed components for maximum rigidity. The connection points for thruster control and sensor information are provided by Blue Robotics penetrators positioned on the aluminum center chassis.
These penetrators are all M10 thread penetrators that have been sealed with marine-grade epoxy while still allowing the connections to pass through to the hull. The epoxy was set and let to cure for 24 hours to ensure a complete seal. We use these penetrators because of their ease of assembly and how easy they can be replaced if changing or replacing equipment.
Additional connections are provided for external power recharging and a router data connection via wet pluggables.
The wet pluggables serve as a way to recharge Hydrus's batteries or give crucial system updates or monitor the AUV's progress without the need of disassembling the hull via either a direct Ethernet connection or with the use of a wireless buoy. This reduces the wear of its interior components.
Many of the components utilized were manufactured before the onset of the COVID-19 pandemic, but most were manufactured or acquired after, and all were assembled after. The team made full use of 3D printer technology in order to make test pieces and the final components from the safety of our individual homes.
The 3D printers utilized were a Snapmaker 2.0 A250 that was used to print any PLA component or fit test, and a Creality Ender 3 that was heavily modified with a higher heat capacity extruder to allow it to successfully process the carbon fiber reinforced filament. The filaments used were 3D Fuel's line of Pro PLA filaments and CarbonX's ABS plus carbon fiber filament.
Pressure tests to ensure the rigidity of the seals and waterproofing were conducted with vacuum compressors by bringing Hydrus's internal pressure to 14.7 psi vacuum, effectively simulating a depth of 33 feet, and maintaining it overnight, which is more than enough for the competition.
This metric was determined by assuming the pressure differential between a vacuum and outside air environment acts in the same way as it does underwater. Another assumption was that seals which are airtight are also waterproof. We recognized that these were merely assumptions, so when the opportunity presented itself, we also did live tests in the university's pool. Pressure tests in the pools were all done with no electronics present within the hull in order to avoid any unforeseen accidents.
Destructive tests were improvised with weights to confirm the ability of the 3D printed components to withstand the forces generated by the thrusters and the HDPE chassis's rigidity.
Destructive tests included impact resistance tests, tensional strength tests, and static load bearing tests. These were mainly focused on the 3D printed components due to the unstable and anisotropic nature of printed parts. This means that parts could not withstand stress in a uniform manner along its volume. These tests allowed us to find the optimal print orientation for each component that would allow the stress distribution to match the needs of the AUV.
When it was allowed, the team was able to take hydras to the university pool in short squads of 3 members while taking the appropriate health safety measures to avoid contamination, while also being supervised by lifeguards. In the future, we hope to be able to test hydras' capabilities more often and with greater rigorous tests.